Far beyond Earth, orbiting the gas giant Saturn, lies a tiny, icy moon that has captured the attention of scientists and dreamers alike. Enceladus is only about 505 kilometers across, making it much smaller than our own moon, yet beneath its glittering ice crust lies something extraordinary, a global ocean of liquid water. This hidden ocean makes Enceladus one of the most promising places in the solar system to search for extraterrestrial life. The story begins in 2005, when NASA's Cassini spacecraft, while flying past Saturn, captured something unexpected at Enceladus's south pole. Towering geysers of water vapor and ice particles were venting hundreds of kilometers into space from fractures in the surface known as the tiger stripes. This was the first strong evidence that liquid water existed far beyond the traditional habitable zone of the solar system. Not only that, but Cassini's instruments revealed that the south polar region was warmer than expected, up to 200 Kelvin at the fractures, far higher than the frigid environment around it. The heat flux measured implied an energy output of several to over 10 gigawatts, a value far too high to be explained by sunlight alone. Instead, it pointed to tidal heating, the immense gravitational tug-of-war between Saturn and its other moons, keeping the ocean liquid and active. But the real revelations came when Cassini flew directly through the plumes. Its mass spectrometer showed that the vapor was about 98% water, but it also contained carbon dioxide, methane, ammonia, and, crucially, molecular hydrogen. That hydrogen is a chemical fingerprint of water-rock interactions at the ocean floor. On Earth, such processes occur through serpentinization, where water reacts with iron-rich rocks to produce hydrogen. At hydrothermal vents on our own seafloor, hydrogen serves as an energy source for entire ecosystems of microbes. The ice grains in the plumes told an equally compelling story. They contained sodium salts and carbonates, proving that Enceladus's ocean is salty, like Earth's. Even more intriguing were microscopic silica nanograins, which can only form when hot alkaline fluids from hydrothermal vents encounter colder ocean water. These particles suggested that not only is there an ocean, but that the ocean floor is geologically active, with vent systems possibly reaching temperatures above 90 degrees Celsius. In other words, the same kinds of environments where life thrives on Earth may exist deep beneath Enceladus's ice. Cassini also found complex organic molecules with masses greater than 200 atomic units. These were not just simple gases like methane, but large carbon-based structures resembling fragments of biological macromolecules. In 2023, reanalysis of the plume data revealed yet another crucial ingredient: abundant phosphorus, locked in sodium phosphates. Phosphorus is often scarce in extraterrestrial environments, but it is essential for life on Earth, forming the backbone of DNA, RNA, and cell membranes. In fact, the concentrations inferred for Enceladus may even exceed those in Earth's oceans. Taken together, water, organics, energy, and nutrients, these discoveries paint a picture of an ocean world that checks nearly every box for habitability. The chemistry of that ocean appears to be moderately alkaline, with pH estimates between 9 and 12. This alkalinity is consistent with ongoing serpentinization, and it provides a stable environment for organic molecules. It also sets the stage for possible biological metabolisms. The reaction of hydrogen and carbon dioxide to form methane is one of the simplest and most ancient forms of metabolism on Earth, carried out by microorganisms known as methanogens. Experiments simulating Enceladus's conditions show that such reactions could proceed in its ocean, meaning that if life ever emerged there, it would have access to both food and energy. Still, the presence of organics and methane alone does not prove life. Abiotic chemistry can produce these molecules as well, through catalytic reactions on mineral surfaces or through hydrothermal processes without biology. To truly distinguish life from non-life, scientists would need multiple lines of evidence. Isotopic measurements, for example, could reveal the subtle fractionations characteristic of metabolism. Molecular patterns, such as specific amino acid distributions or lipid structures, might betray biological origins. Even the detection of enantiomeric excess, where one-handedness of molecules dominates, would be a powerful sign, since life on Earth universally selects one chirality. Cassini, while revolutionary, did not carry the instruments capable of detecting such biosignatures. But future missions are being designed with exactly that in mind. The concept known as the Enceladus Orbilander has been highlighted as a top priority for the coming decades. This mission would first orbit Enceladus, flying repeatedly through its plumes with next-generation mass spectrometers before landing on the surface to analyze freshly fallen plume particles. It would carry the tools necessary to search directly for complex biomolecules, isotopic signatures, and even cellular structures. If approved and launched, it could arrive in the mid-21st century and finally answer the question that Cassini left hanging: is there life on Enceladus? In the meantime, scientists on Earth are not waiting. Laboratory experiments are underway to replicate Enceladus-like conditions, from alkaline oceans to hydrothermal vent chemistry. By studying what types of molecules form spontaneously in such settings, researchers hope to define the thresholds that would distinguish biology from abiotic processes. This groundwork will guide the instruments of future missions and sharpen our ability to recognize true biosignatures. When you step back and consider the evidence, Enceladus is extraordinary. It has a liquid ocean in direct contact with a rocky core. It has ongoing hydrothermal activity. It has organics, salts, and even abundant phosphorus. It has chemical energy sources and favorable conditions for metabolism. Everything we know suggests that Enceladus is not just habitable in theory, it is habitable in practice. Whether or not life has taken hold, there remains the great unanswered question. But unlike in the past, this is no longer speculation. It is a question we can test. The discovery of microbial life on Enceladus would change everything. It would show that life is not unique to Earth, that biology can emerge wherever conditions are right, even in the frozen darkness of the outer solar system. And if life arose independently on both Earth and Enceladus, then the universe might be teeming with it. For now, we wait, we simulate, and we plan. The search continues, not for little green men, but for tiny microbes swimming in an alien sea, hidden beneath the ice of Saturn's most mysterious moon.